Algebra, lecture 3. We started to talk about permutations on Monday, and we'll talk about them more today. They are very important in algebra and in group theory. They have to do with something, in principle, very simple, just the symmetries of a set of n points or n numbers. Any questions before we start? I'm going to begin by reviewing what we did on Monday, but are there any questions? Any issues you have? Okay, let's see. Let me just change the view for one moment. Okay, so we consider permutations are what? What is a permutation? It's a way, you can think of it visually as you have the numbers 1, 2, 3 up to n, the first n positive integers, and we're going to rearrange them. So we're going to put the numbers in order, put the numbers in a sequence, but we're going to change the sequence. So maybe 1 will become, I don't know, let's say we're going up to 6. Maybe 1 will become 5, and 2 will become 3, and 3 will become 1, and 4 will stay at 4, and 5 will go to 2, and 6 will stay at 6. So now 5, 3, 1, 4, 2, 6 is some arrangement or permutation of the numbers 1 through 6. And we can think of this as a function, just like in calculus, only easier, a function from the set of numbers to itself. And it's not just any function. You couldn't send every number to 5, for example. It has to be 1 to 1. So 2 different numbers get sent to 2 different numbers. And then it's automatically what is called onto, which means if you send every pair of numbers to different numbers, then the image has to be the numbers you started with, all of the numbers, just in a different order. And that's a permutation. And what is the standard notation for a permutation? Let's say we call this function, this permutation sigma. We write 1, 2, 3, 4, 5, 6, and where each number gets sent to. So in this example, sigma of 1 is equal to 5. We put a 5 here. Sigma of 2 is 3, so we put a 3 here. Sigma of 3 is 1. 3 goes to 1. Sigma of 4 is 4. Sigma of 5 is 2. Sigma of 6 is 6. So this is the standard notation that we use for a permutation. Okay. Any questions about that? Let's say we have another permutation. Let's call it tau. Another permutation of the numbers 1 through 6. And let's say tau is a cyclic permutation that sends each number to the next number. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6. There's no 7, but we can send 6 back to 1. So that's the permutation tau. And again, this is a function, 1 to 2, 2 to 3, and so forth. And this is very important. We can multiply permutations. So multiplication of permutations means exactly, just as in calculus, composition of functions. So, for example, what is sigma tau of 1? This means sigma of tau of 1. Tau of 1 is 2. So that's sigma of 2. Sigma of 2 is 3. So if we write sigma tau in the standard form 1, 2, 3, 4, 5, 6, 1 ends up at 3. What is sigma tau of 2? That's sigma of tau of 2. Tau of 2 is 3, so that's sigma of 3. What is sigma of 3? It's 1. So sigma tau sends 2 to 1. What is sigma tau of 3? So tau sends 3 to 4, and sigma sends 4 to 4. So sigma tau of 3 is equal to 4. What is sigma tau of 4? So tau of 4 is 5. Sigma of 5 is 2. What is sigma tau of 5? Tau sends 5 to 6, and sigma sends 6 to 6. So we end up at 6. What is sigma tau of 6? Tau sends 6 to 1, and sigma sends 1 to 5. So sigma tau is the permutation 314265. Okay. Any questions about this? This is a basic calculation you have to learn how to do in algebra. So let me just stick with these two permutations for the moment. So sigma is the permutation 1, 2, 3, 4, 5, 6, and 5, 3, 1, 4, 2, 6. And tau is the permutation 1, 2, 3, 4, 5, 6, and 2, 3, 4, 5, 6, 1. So we just calculated sigma tau, and we got 314,265. What about tau sigma? So this means you apply sigma first and then tau. So what is tau sigma of 1? Sigma sends 1 to 5, and tau sends 5 to 6. So tau sigma of 1, you end up at 6. Any questions about this? So take a minute. You should have paper and pencil or paper and pen in front of you, and calculate the tau sigma. What are the numbers that you fill in this 2 by 6 matrix? What are the numbers that go in here? Spend a minute and calculate it. So can someone tell me, what does the number 2 get sent to?
I put 4.
Let's see. So
Oh no,
sigma
is that 3?
sends 2 to 3,
It's
and
one.
tau sends 3 to 4, so that's 4.
Uh,
Where does 3 go?
3, I put 2.
Okay, good. Where does 4 go?
I put 5.
See, 4 goes to 4 goes to 5. Excellent. Can someone
Uh,
else tell me where 5 goes? So sigma sends 5 to 2, and tau sends 2 to 3. And sigma sends 6 to 6, and tau sends 6 to 1. So tau sigma is this permutation. And if you compare these two permutations or these two functions, they're different. Sigma tau sends 1 to 3, tau sigma sends 1 to 6. So sigma tau is not equal to tau 6 in this case. And the way we say this in mathematical language is multiplication of permutations is not commutative. You know, if you have numbers, 3 times 2 equals 2 times 3. Multiplication of numbers is commutative, but multiplications of permutations is not. It may happen in special cases, it is, but in general, it's not true. So you can't, if you're solving a problem in algebra and you have sigma tau, you cannot replace it with tau sigma. Okay. Now, we talked about different kinds of permutations or operations on permutations. We have what are, for example, cycles. So let's give an example of a cycle. Suppose we look at tau. Tau try and get it on the page. Here's tau. Tau sends 1 to 2, sends 2 to 3. It sends 3 to 4. It sends 4 to 5, 5 to 6, 6 back to 1. So if we follow the trajectory of any number under iterations, repeated multiplications or applications of tau, we have 1 to 2 to 3 to 4 to 5 to 6 back to 1. This is an example of what's called a cycle. It's a permutation or part of a permutation that sends numbers from one to another, and then back where it starts without any repetitions. So this is an example of a cycle. Let's look at the permutation, and you notice this cycle includes all the numbers. So one way of writing a cycle is just as a sequence of, in this case, 1, 2, 3, 4, 5, 6. This means 1 goes to 2, 2 goes to 3, 3 to 4, 4 to 5, 5 to 6, and 6 back to 1. So this is cyclic notation for a permutation. Let's look at sigma. In sigma, 1 goes to 5, 5 goes to 2, 2 goes to 3, and 3 goes back to 1. So 4 and 6 don't occur in this cycle.
We can see that. Okay.
If you look at 4, sigma sends 4 to 4. And sigma sends 6 to 6. So the cycle 1, 5, 2, 3, we can also write as 1, 5, 2, 3 like that. This sort of trivial cycle, 4 goes to 4, that's just 4 goes to itself, and 6 goes to itself. So using cyclic notation, we can also write sigma in this form. And usually we would just write 1, 5, 2, 3, because if you don't have a 4 or a 6 here, that just means 4 goes to itself and 6 goes to itself. Right. Let's look at sigma tau and tau sigma and write them in cyclic notation. So here is sigma tau. Let's see, in sigma tau, 1 goes to 3, 3 goes to 4, 4 goes to 2, and 2 goes back to 1. So that's the cycle 1, 3, 4, 2. What about 5 and 6? 5 goes to 6, and 6 goes back to 5. So we have another cycle. This cycle has 4 numbers in it, or has length 4. This cycle has 2 numbers in it, or length 2. So we could say that sigma tau in cyclic notation involves these 2 cycles. And notice the numbers here are different from the numbers here. So these are called disjoint cycles. 2 cycles are disjoint if they involve different numbers. Let's look at tau sigma. So here's tau sigma. 1 goes to 6, and 6 goes back to 1. So that's the cycle of length 2, 1, 6. Let's see, what's the next number? 2. 2 goes to 4. 4 goes to 5. 5 goes to 3. And 3 goes back to 2. So this is a 4 cycle. 2, 4, 5, 3. So this is tau sigma in cyclic notation. And we can make several observations about cycles. First of all, the cycle 1, 6, that sends 1 to 6 and 6 to 1. The cycle 6, 1 sends 6 to 1 and 1 to 6. It's the same thing. These are the same permutation. If I take 1, 3, 4, 2, here's a picture of it. 1 goes to 3, goes to 4, goes to 2. It's also the case that 3 goes to 4, goes to 2, goes to 1. It's the same permutation. They both send 1 to 3, 3 to 4, 4 to 2, and so forth. I could start here. This is 2 goes to 1, goes to 3, goes to 4. Let's start here. 4 goes to 2, goes to 1, goes to 3. So these are exactly the same cycles or the same permutations, because these are functions. They tell you what gets sent where. In each of these, 4 goes to 2, and so on. Okay, any questions about that? So here, let me just, as an example for something for you to do right now, suppose I take sigma to be a permutation of the numbers from 1 to 12. And I'll just write these numbers down more or less at random. Let's see, what numbers haven't I used yet? I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here is a permutation of 12. This is in, this means in, this symbol means in, S12. S12 means all permutations of the first 12 numbers. So here's a permutation in S12. Write it as a product of disjoint cycles. Oops, I might be missing something. 1, 2, 3, 4, 5, 6, 7, 8. I need a 9. 9, 10, 11, 12. Good. Now I have a permutation. So write this as a product of disjoint cycles. And I'll pause for a moment while you do that. Resume. So 1 goes to 5. 5 goes to 3. 3 goes to 6. 6 goes to 11.
And 4.
11 goes to 4. And 4 goes back to 1. So this is a 6 cycle, a cycle of length 6. Let's take a number that's not in here. Doesn't matter which one I take. I'll take the smallest, which is 2. See, 2 goes to 12. 12 goes to 7. 7 goes to 8. 8 goes to 10. 10 goes to 9. And 9 goes back to 2. So sigma, this is a product of 2 disjoint 6 cycles. The numbers here are different from the numbers here. That's what disjoint means. And each of them happens to have 6 numbers in it. So each of them is a 6 cycle. So this is the permutation sigma in cycle notation. Any questions about that? Okay. Yeah. Let me stick with sigma for the moment. Or I don't have to stick with sigma. Let's take another permutation. Suppose I take a permutation 1, 2, 3, 4, 5, 6. Let me take a permutation in S7. Say 2, 7, 1, 3, 6, 4, 5. That's a permutation. Again, I'll call it sigma. So sigma, for example, sends 1 to 2, and so forth. 2 to 7, 3 to 1. Now, for every permutation, there's an inverse. So the inverse of sigma is a permutation. Write it as sigma to the power minus 1. This is called sigma inverse in S7. And again, it's just like what you learned in calculus. In calculus, you might have had the function f of x equals e to the x. And the inverse of this was the natural log of x. Because if you took f composed with f inverse of x, this meant f of log of x, which is e to the log x, which is x, sends x back to itself. And f inverse f of x was f inverse of e to the x, which is the log of e to the x, which is x. So f composed with f inverse and f inverse composed with f, this was just the identity function, sends x to x. Now, in the permutation, the set of permutations Sn, the permutation which we call E, which sends every number to itself. So this is the identity permutation. And for every permutation sigma in Sn, there is a permutation sigma inverse in Sn, such that when you multiply sigma times sigma inverse, or sigma inverse times sigma, you get the identity permutation. So let's try to figure out what that is. So if you apply sigma to a number A and you get B, then sigma inverse has to send B back to A. That's the only way you get the identity. So for this permutation sigma, what would the inverse be? That's going to be some permutation in S7. Let's
1
see.
goes to 3.
So sigma sends 3 to 1. So the inverse has to send 1 back to 3.
2 back
Sigma
to
sends
1.
1 to 2. So the inverse has to send 2 back to 1. Sigma sends 4 to 3. So the inverse has to send 3 back to 4. 6 goes to 4, so 4 has to go back to 6. 7 goes to 5, so 5 has to go back to 7. 5 goes to 6, so 6 has to go back to 5. And 2 goes to 7, so 7 has to go to 2. So this is sigma inverse. That's the inverse of the permutation.
Professor, for the inverse, is that oh, okay. 1 goes to 3?
In the inverse, yeah, because sigma sends 3 to 1, so the inverse has to send 1 back to 3. So 1 goes to 3.
And then it says 2 goes to 1?
Well, sigma sends 1
Oh,
to
got
2,
it, got it.
so
got it.
2 has to get sent back to 1.
Thank you, I got it now.
Okay. So we just observe some properties of Sn. So Sn is the set of all permutations of the numbers from the positive integers from 1 up to n. So first of all, we have an operation of multiplication of permutations. Right. Right. We can multiply permutations. Multiplication, and this is really just composition of functions. Multiplication is associative. Again, you saw this in calculus. What this means is if you have 3 permutations, say rho sigma tau in Sn, then if I multiply rho sigma, I get a new permutation, and I can multiply that by tau. Or I can multiply sigma tau and take rho and multiply rho by sigma tau, and these are always equal. So this is called the associative law for multiplication of permutations, and multiplications associative. Third property is there is an identity permutation, E in Sn, and E has the property that E times sigma and sigma times E is sigma for every permutation in Sn. Because let's say if sigma sends 3 to 7, E sends 7 to 7. It sends everything to itself. So it doesn't change the permutation at all. This is the identity. It's just like multiplying a number by 1. It never changes the number. And the fourth property is, we might call it existence of inverses. For every sigma in Sn, there is a permutation sigma inverse in Sn, such that sigma times sigma inverse, or sigma inverse times sigma, they commute, is equal to the identity. So Now, in general, we will see over and over again many examples in this course of sets that have some multiplication, or it might be addition, but some binary operation. There's some multiplication that's associative, has an identity, and every element has an inverse. And a set with such a property is called a group. So let's just write Sn is an example, a very important example of what is called a group. And we'll talk about that much more later, but this is just to point out that a set with a multiplication that satisfies these properties is what we mean in mathematics by a group. Okay. And just so you know, this is not unusual. Suppose we take GB to the set of all positive numbers, positive real numbers. Positive means strictly greater than 0. So if you have two numbers, x and y, you can multiply them. You can multiply numbers, and they teach you in elementary school that xy times z is the same as x times yz. So multiplication of positive numbers is associative. And there's an identity, it's the number 1. 1 is positive. 1 times x and x times 1 is always equal to x. And if you have any positive number x, its reciprocal 1 over x is still positive, and x times 1 over x, or 1 over x times x, is equal to 1. So the inverse of x in the real numbers is the number 1 over x in the positive real numbers. So the positive real numbers with ordinary multiplication is another example of a group. Let me just state, so Sn is a group. And the other important fact that we've observed is that every permutation sigma in Sn is a product of disjoint cycles. That is, we had an algorithm, a method, given a permutation to write it as a product of disjoint cycles. And I should say that disjoint cycles commute. For example, suppose I have the cycle 1, 4, 5, 2, and the cycle 3, 7, 6. So 1, 4, 5, 2, 3, 7, 6, they involve different numbers. So these are permutations in S7. So let's say in S7, we have this cycle and this cycle, and we look at this product. Let's call this sigma. So let's see, what is this? 1, 2, 3, 4, 5, 6, 7. Let's calculate this. So this sends 3 to 7, and there's no 7 here. That means 7 goes to 7, so 3 goes to 7. Well, actually, let's follow around. Let's say 1. This sends 3 to 7, 7 to 6, 6 to 3, and doesn't move anything else. So this sends 1 to 1, and then this sends 1 to 4. There's no 2 here, so this sends 2 to 2, and this sends 2 to 1. There's no 4 here. 4 goes to 4, and this sends 4 to 5. There's no 5 here, so 5 goes to 5, and this sends 5 to 2. There is a 6 here. 6 goes to 3. There's no 3 here, so 3 goes to 3, so 6 ends up at 3. This sends 7 to 6 to 6. So if I write the disjoint cycles in this order, this is the permutation. Suppose I write them in the opposite order. This sends 1 to 4, and this sends 4 to 4. This sends 2 to 1, and this sends 1 to 1. 3 goes to 3, goes to 7. 4 goes to 5, goes to 5. 5 goes to 2, goes to 2. 6 goes to 6, goes to 3. 7 goes to 7, goes to 6. And if you compare these two, you see 4, 1, 7, 5, 2, 3, 6, 4, 1, 7, 5, 2, 3, 6. They're exactly the same. So the order in which I wrote these cycles doesn't matter because the cycles are disjoint. If they weren't disjoint, it would be different, but the products of disjoint cycles commute. All right. Any questions about this? Okay. So I want to look at some of the exercises. So this is exercise 1.5.1. To work out the full multiplication table for the set of permutations of 3 objects. So what are the permutations of 3 objects? So this is the group S3, all permutations of 3 objects. Now, of course, there's always the identity that sends
1, 2, 3.
1 to 1, 2 to 2, and 3 to 3. Okay. There's the permutation, let's call it sigma, that sends 1 to 2, 2 to 3, and 3 back to 1. There's the permutation.
We are going to have 6 permutations, so we can name as A, B, C, D, O.
Yeah, right, there are lots of them. So what other permutations are there? There's, you could send 1 to 3, 3 to, 2 to 1, and 3 to 2. That's another permutation. We could have the permutations. So these 2 permutations, everything gets moved. In this permutation, nothing gets moved. We could have the permutation that only moves 2 things. So you could keep 1 fixed and interchange 3 and 2. Or you can keep 2 fixed and interchange 3 and 1. Or you can keep 3 fixed and interchange 2 and 1. So, and if you try to find more permutations, you can't. There are exactly these 6 permutations.
That can be calculated like n factorial over n minus factorial, right? N minus 1 factorial. So possible
Well,
permutations that we can get.
I'm not sure why you want to do it at this point, but in any case, these are all the permutations of 3 numbers. So let's see, here I fixed 1, I'll call this tau 1. Here I fixed 2, I'll call this tau 2. Here I fixed 3, I'll call this tau 3. Let me call this rho. Okay. So these are all the permutations, and we want to work out the multiplication table. That means what are all the pairwise products of these 2? So I have E, sigma, rho, tau 1, tau 2, tau 3, E, sigma, rho, tau 1, tau 2, tau 3, and I want to write the multiplication table. That means I have to fill out this box. So I have 6 times 6, I have 36 products I have to figure out. So let's see. Some of these are easy to figure out because if you multiply, so what I'm going to put in each box is this times this. So this will be E times E, which is E. This will be E times sigma, but multiplying by E, the identity doesn't change what you're multiplying. So this is sigma. E times rho is rho. E tau 1 is tau 1. E tau 2 is tau 2. And E tau 3 is tau 3. So the first row is easy to get, and this first column is easy to get. This is E times E. This will be sigma times E, which is sigma. Again, if you multiply on the left or the right by the identity, doesn't change anything. So rho times E is rho. Tau 1 times E, tau 2 times E, tau 3 times E. Okay. So I just filled in 11 of these boxes. I have 25 left. Right. What goes here? Sigma times sigma. That's sigma squared. What is sigma squared? That means you do sigma followed by sigma. So let's actually do this little calculation. What is sigma squared, or sigma times sigma? Sigma sends 1 to 2. Apply sigma again. 2 goes to 3, so 1 goes to 3. Sigma sends 2 to 3, and then 3 to 1, so 2 goes to 1. Sigma sends 3 to 1, and then sigma again sends 1 to 2. You get 3, 1, 2. That's rho. So sigma squared is equal to rho. Right? What's sigma times rho? So rho sends 1 to 3, and sigma sends 3 back to 1. Rho sends 2 to 1, and sigma sends 1 to 2. Rho sends 3 to 2, and sigma sends 2 to 3. So sigma times rho is this permutation, which is the identity. So the identity goes there. What goes here? Sigma times tau 1. That's, so what is that? Tau 1 sends 1 to 1, and then sigma sends 1 to 2. Tau 1 sends 2 to 3, and sigma sends 3 to 1. Tau 1 sends 3 to 2, and sigma sends 2 back to 3. So sigma tau 1 is the permutation 2, 1, 3. That fixes 3 and interchanges 2 and 1. That's exactly tau 3. Right. And you just have to continue and fill in all the boxes. What is it goes in here? This is tau 1 times tau 1. So tau 1 fixes 1, interchanges 2 and 3. If you do it again, fixes 1. If you interchange 2 and 3 again, you're back to where you started. So tau 1 squared, tau 1 times tau 1 is the identity. And similarly, tau 2 squared is the identity, and tau 3 squared is the identity. And it's worthwhile doing this whole exercise carefully, because you get you acquire a feel for what these operations in products of symmetric products of permutations look like. Okay. All right, let's look at a couple more. So those we look at 1.5.3. I have the permutation 1, 2, this is part A. 1, 2, 3, 4, 5, 6, 7, 2, 5, 6, 3, 7, 4, 1. And we want to write this as a product of disjoint cycles. So we can say 1 goes to 2, 2 goes to 5, 5 goes to 7, 7 goes back to 1. So I have a 4 cycle. And 3 goes to 6, 6 goes to 4, 4 goes back to 3. So this is in S7. It's a permutation of the first 7 numbers. And this permutation is a product of two disjoint cycles, a 4 cycle and a 3 cycle. Okay. Let's look at part B. I have a 2 cycle and a 5 cycle. These are not just joined because 1 and 2 is in both of them, but this is still some permutation of 1 through 5. So let's work out what that permutation is. We go from right to left. So this is 1 goes to 2 and 2 goes back to 1. 2 goes to 3 and 3 goes to 3. 3 goes to 4, 4 goes to 4. 4 goes to 5, 5 goes to 5. 5 goes to 1, 1 goes to 2. So the product of these 2 cycles is this. And what is this as a product of disjoint cycles? 1 goes to 1. Don't even have to write that then. 2 goes to 3. 3 goes to 4. 4 goes to 5. 5 goes back to 2. Sorry. 2 goes to 3. 3 goes to 4. 4 goes to 5. And 5 goes back to 2. So this permutation is a 4 cycle. Let's look at G. G is 1, 2, 1, 3, 1, 4. So this is some permutation of 1, 2, 3, and 4. And see, this sends 1 to, they're not disjoint. This sends 1 to 4, to 4, to 4. This sends 2 to 2, to 2, 2 to 1. This sends 3 to 3, 3 goes to 1, 1 goes to 2. This sends 4 to 1, 1 to 3, 3 to 3. So the product of these 2 cycles is this permutation. And if I write this in cycle notation, 1 goes to 4, 4 goes to 3, 3 goes to 2, 2 goes back to 1. So this permutation is a 4 cycle. Let's do one more. These are kind of fun. Suppose I have 1, 3, 1, 2, 3, 4, 1, 3. So these are not disjoint, so you can't rearrange them. This is some permutation of 1, 2, 3, and 4. So 1 goes to 3, 3 goes to 4, 4 goes to 4. 2 goes to 2, 2 goes to 3, 3 goes to 1. 3 goes to 1, 1 goes to 2, 2 goes to 2. 4 goes to 4, 4 goes to 1, 1 goes to 3. So this, in standard notation, is the permutation 4, 1, 2, 3. And in cycle notation, 1 goes to 4, goes to 3, goes to 2, goes back to 1. So this permutation is also 1, 4, 3, 2. So this cycle, a 4 cycle, can be written in different ways as products of cycles. They're just not disjoint cycles. And just because you'll hear this term often, a 2 cycle is sometimes called a transposition. A two-cycle AB sends A to B and B back to A. It just transposes A and B. So another name for a two-cycle in algebra is a transposition. And problem 1.5.5, which I want you to have a chance to think about, I'll do it on Monday, is to show that if you take any k cycle, you can always write it as a product of k minus 1 two cycles. So here's an example. Here's a 4 cycle, and it's a product of 3 two cycles. So in particular, this says if you have any 3 cycle, you should be able to write it as a product of 2 two cycles. And let me just see if I can make a lucky guess. 1, 3, 1, 2. This sends 1 to 2 to 2, 2 to 1 to 3, 3 to 3 to 1. Yeah. So here I just wrote a 3 cycle as a product of 2 two cycles. And suppose I had 3 different numbers, A, B, and C. If I have AB times BC, what is that as a permutation? So this sends A to B, B to C, C to B to A. So this is the cycle that sends A to B to C. So that's kind of interesting. It's almost as if you have A, B, and B, C, you just write it together and squish the B into one thing. This is a rule, actually, that says how you can write any 3 cycle as a product of two cycles. In fact, if I put this in this form, this is the same as 1, 3 is the same as 3, 1. So 3, 1 times 1, 2, that would be 3, 1, 2. And this sends 3 to 1, 1 to 2, 2 to 3. That's the same as 1 goes to 2, goes to 3, goes back to 1. So that's another way of saying that. Let's just make one other remark. Let's ask the question, how many permutations are in Sn for any positive integer n? So let's look at some examples. S1, this is just permutations of a number 1. Well, the only way you can permute 1 is 1 goes to 1. So S1 just consists of the permutation 1 goes to 1. So the number of elements in S1, so I'm going to write Sn in absolute value signs is the number of permutations in Sn. So I don't have to keep writing all those words. So the number of permutations in S1 is 1. What about S2? So you have permutations of 1 and 2. Well, there are only 2 possibilities. You have the identity, 1 goes to 1 and 2 goes to 2. And then the other alternative is 1 goes to 2 and then 2 has to go to 1. So the number of permutations in S2 is 2. What about S3? Well, I actually calculated all the permutations of S3 a moment ago, and we saw there were 6. So it's a very important fact in algebra that the number of permutations in Sn is usually written as n with an exclamation point. This means the product of all the integers up to n. This is called n factorial. And the number of permutations Sn in Sn is always n factorial. Let's look at these three examples. 1 is 1 factorial, just 1 times 1. 2 is 1 times 2, which is 2 factorial. 6 is 1 times 2 times 3, which is 3 factorial. If we tried to calculate S4, we would find 24 permutations. 24 is 1 times 2 times 3 times 4, which is 4 factorial. So it's just an important algebraic fact that the factorial number tells you how many permutations there are of the integers from 1 up to n. And so let's say I want to prove this, and I'm going to prove it by proving something slightly more general. So Sn is the number of permutations of the numbers from 1 up to n. But instead of the numbers from 1 up to n, you can think of a set where you have n different objects, x1, x2, x3 up to xn, and a permutation is just some arrangement of them. So if sigma is in Sn, you could have x sigma of 1, x sigma of 2, x sigma of n. So for example, a permutation of x1, x2, x3, x4 might be x4, x1, x3, x2. It's the same objects in a different order. And there's no difference in counting permutations of n objects or permutations of the particular n objects that are the first n numbers. So we know that this statement that Sn has n factorial permutations in it, this is true for n equal 1, 2, and 3, because that's what I just calculated. That's exactly this. S1 has 1 factorial, S2, 2 factorial, S3, 3 factorial. So this statement is true for 1, 2, and 3. So how do we prove this is true in general? So let's assume that Sn minus 1 is n minus 1 factorial. And I will show that this implies that Sn has n factorial permutations. So if you look at all the permutations in Sn, I can divide this into n different subsets, depending, for example, on where the number 1 gets sent.
Professor, can you move up?
So remember, Sn, 1, 2 up to n goes to A1, A2 up to A sub n. This is just the numbers 1 through n in some order. Let's look at where 1 gets sent. So how many permutations send 1 to some number A1? Well, if 1 goes to A1, then 2 up to n, these get mapped into the numbers, all the numbers different from A1. All the numbers from 1 up to n that are not equal to A1. So this is a map from n minus 1 objects to n minus 1 objects. And what one calls the inductive hypothesis says the number of these kinds of maps is n minus 1 factorial. It's just like the number of permutations of n minus 1 objects. So for every choice of A1, we have n minus 1 permutations, and there are n choices of A1. So the number of permutations is going to be n times n minus 1 factorial. And n times n minus 1 factorial is exactly n factorial. Because this is the product of the numbers from 1 up to n minus 1, times n is the product of the numbers from 1 to n. So we'll come back to this later, but it's nice to begin to see what a proof in algebra is going to look like. This is a proof using what is called mathematical induction. We assume that a certain statement is true for n minus 1, and then we prove that it's true for n. So that means if it's true for 1, it's true for 2. If it's true for 2, it's true for 3. If it's true for 3, it's true for 4, and so on forever. And that's a proof. So this is a proof by mathematical induction that the number of permutations of in Sn is exactly n factorial. And if you are studying the text, as you should be, right, you're responsible not just for what I talk about in these lectures, but also what is in the book. And we're doing all of chapter 1, basically. In this discussion of permutations, there's a footnote that says mathematical induction is discussed in Appendix C. And since you have the book, you should study Appendix C. It also says there's another footnote. This is on page 22. The cardinality of a finite set. Cardinality is just another way of saying the number of elements of a finite set of a set X is denoted by X with absolute value signs around it. So Sn with these absolute value signs or straight lines around it means the cardinality or the number of elements in this set, and that's equal to n factorial. Okay. All right, so we've done a lot today, and I don't want to push ahead too fast. So on Monday, I'm happy to answer questions about homework problems. I also have problem sessions this week again. I had one on Monday. There's another today at 1 o'clock, and one on Friday morning at 11 o'clock. So I'm happy to answer questions or work out problems for you. And on Monday, we begin section 1.6 on divisibility in the integers. And I would strongly recommend that you read section 1.6 before class on Monday, because it's always good to have some idea what we're talking about before we start to talk about it. That's kind of prudent. It's just like athletic teams sending scouts to see how the other side plays before the game. So you can scout ahead and see what's going on in section 1.6 before we start to talk about it on Monday. Okay. Questions about this? Any questions? If not, then we will quit at this point. And in a short time, I will post the lecture on YouTube if there's anything you want to review. Okay.
Thank you, Professor. Have a nice day.
Okay. All right. Be well. Have a good weekend. Survive the snow. Not too much. A little bit of snow. All right. Bye, all.
Bye, Professor.
Okay, bye.